You can buy a packet of Maggi noodles almost anywhere in the world for about 30 cents. It is a highly accessible source of calories, requiring only boiling water and a few minutes of time. Maintaining this low price point requires a billion-dollar industrial ecosystem. The facility operates at a scale where margins of error are measured in microns and seconds. This diagram shows a standard industrial pipeline layout. In a facility like this, a single millimeter of error in a mechanical cut or a fluctuation of a fraction of a degree in heat triggers a halt across the entire automated sequence. The engineering challenge is to take thousands of tons of dry flour and water and force them into a repeatable geometric architecture. Preparing a packet of Maggi is the final step in a chain of high-precision manufacturing. Every block is the result of a system that allows no deviation from its programmed design. The process begins with raw particulate materials. Mountains of dry wheat flour and thousands of gallons of water are stored in silos before being fed into the mixing stage. Blending these elements require massive, unyielding steel arms. These high-torque rotors apply constant pressure, forcing the powder and liquid to bond into a single mass. This chart maps the volumetric liquid-to-solid ratio. To achieve the correct hydration, the mixture must hit a specific percentage window. If the ratio shifts, the material will either crumble into dust or turn into an unworkable sludge. The objective is viscoelasticity. The material is worked until it becomes a stretchable, methodical solid that can withstand the tension of high-speed machinery. This initial phase turns unpredictable raw ingredients into a compliant, mathematically consistent material ready for extrusion. The dough moves out of the mixing vats and onto the extrusion line. The slow rotations of the blenders are replaced by a high-velocity kinetic sequence. The dough is subjected to intense pressure and forced through micro-perforated plates, emerging as hundreds of individual, continuous strands. This schematic illustrates the mechanism creating the signature wave. Velocity arrows show the vertical extrusion rate is faster than the conveyor belt, forcing strands to ripple and fold. This geometry provides structural integrity, creating consistent gaps allowing air and heat to flow evenly. The continuous ribbon of rippled dough reaches high-speed robotic blades. These mechanical components divide the moving mass into individual, uniform serving blocks. The blades must operate at staggering speeds. They are programmed to slice through the material in milliseconds without compressing the fragile, freshly extruded structure. This phase uses speed and geometry to maintain total uniformity across millions of units. After being cut, the dough blocks are routed directly into high-temperature deep frying chambers. Inside the fryers, the blocks are submerged in boiling oil. The dough is subjected to an immediate thermal shock, initiating a rapid molecular exchange. This cross-section demonstrates thermodynamic displacement. Heat causes H2O molecules to violently boil out as steam. As moisture escapes, lipid molecules rush in, filling the newly created voids. This displacement hardens the dough matrix, locking the wave geometry into a rigid, permanent state. Removing the moisture also prevents biological decay. Without water inside the structure, the product becomes shelf-stable for months. The fryer is a thermodynamic engine designed to ensure every noodle block remains structurally identical and viable for global distribution. The blocks emerge from the heat and move into cooling tunnels. The process transitions from high-temperature cooking to a clinical, automated packaging sequence. At this stage, the scale of the operation is visible. A river of thousands of identical golden squares moves along the conveyors in perfect unison. The sequence concludes at the packaging line. Plastic film is wrapped and heat-sealed over the block, isolating the product from the atmosphere. This single packet is the result of a sequence involving high-pressure mixing, high-velocity blades, and 150-degree oil. It has been shaped by a system that requires total mechanical compliance. The accessibility of the product is made possible by the rigid application of robotics and thermodynamic control. The engineering ensures that regardless of where it is opened, every block remains an exact copy of the one before it.